So, well, we have conductances and capacitors. So, this is a linear capacitor, right? Just because this capacitor is linear, doesn't mean the current through it has got only a single frequency component. It's embedded inside a time invariant network, time varying network. So, the branch voltage and the branch current will all have these multiple frequencies, right? Okay. If it's linear, let's see what happens, how the currents are related to the voltages. And by the way, a sanity check for this conductance matrix is, what is a sanity check? Exactly. So, if you had a time invariant resistor, right? I mean, just because the network is time varying doesn't mean all resistors will be time varying. You will also encounter resistors which are fixed, right? So, I mean, an obvious thing is that if the resistors are the resistance is fixed, if the conductance is fixed, then all these off diagonal terms will become 0 and you will get a diagonal matrix. Okay. All right. Now we have a capacitance. Again, this is node A and this is node B, and the voltage phasor is VAB minus capital K blah blah blah, VAB 0 blah blah blah, VAB of plus K transpose. All right. And what comment can you make about how is the current phasor now related to the voltage phasor? So, IAB of minus K, IAB of 0, IAB of plus K. How is this related to this guy? Any thoughts? What will be the first row, first column? No, current must be related to voltage in what way? J 2 pi F plus or minus? The voltage is at what frequency? F minus capital KFS. It's a linear capacitor. So, I mean, it's a linear time invariant capacitor. So, this is F minus K capital KFS. What will be the, what would the this thing be, what would the current be? It's simply J 2 pi F minus KFS times C. So, this would simply be, this first term would therefore be J 2 pi F minus KFS times C. Correct? Okay. What comment can you make about the second term in the first row? Well, it's a time invariant capacitor, and therefore the output frequency and the input frequency must be the same. So, all these other entries must be 0. Similarly, the first row in the second column will be 0, and what will you have there? You will have j 2 pi Danish f minus k minus 1 fs 0 and so on. So, this is blah 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 0 0 all the way up to j 2 pi f plus k fs, right. So, therefore, the current phasor can be written as, it is a diagonal matrix, correct, and what all can you remove out of the diagonal matrix as a common factor? J 2 pi c, right, and whatever is left is basically what I will call the F matrix, right, and this is analogous to, if we had a time invariant network, you would see j 2 pi, the scalar f times c. Now you see a vector f, where this F matrix is nothing but j 2 pi, sorry, this is f minus k f s, the rest of it is 0, f minus k minus 1 f s all the way up to f plus capital K Does it make sense? So, all right. So, we have two elements here. So, we know the M&A stamp of this guy, we know the M&A stamp of that guy. The only thing remaining is this one. So, what do you suggest we do? Voltage source. As usual, what do we do? I mean, in a voltage source, what the unknown is, well, the current through the voltage source. Now, you don't not only have to keep track of the current at F, but the currents at all the frequencies that you are interested in, they are all also unknown. So, in other words, in a time invariant network, just that Is was a scalar, now Is is a vector, correct, and likewise the voltage source earlier was a scalar, and you would equate that to one of the node voltages, correct. Now, what do you need to do? Okay, let's actually do this in action. So, let's get back to our voltage source, and this is your G of t. And this is node 1 and this is node 2, and this is the unknown current phasor Is. And what do we do? Well, we now have the usual M&A formulation, except that the entries in this M&A matrix will now all be matrices rather than scalars, right. So, we start with the M&A stamp. So, the unknowns are V1, V2 and Is, right, where it is now understood that V1 will have 2k plus 1 components, V2 will have 2k plus 1 components, and likewise Is will have 2k plus 1 components. And on the right hand side, what do you expect to see? First row, first column, or rather first row in the right hand side is the sum total of currents going into independent currents going into node 1, which evidently we are not putting any independent sources in. So, that will now therefore be a 0 what? It will be a 0 vector with how many entries? 2k plus 1. Likewise, what comment can we make about the second row? It will also be 0, right? And the third row, yeah. So, basically this Vs phasor is nothing but 0, 0, 0. How many zeros will be there? Yeah, there will be capital K zeros, then there will be a 1, and then does it make sense, people? Right. So, as you can see, I mean, the mechanics of the whole process is just the same, right? All that you are doing is now replace the MNA stamp of a time invariant element with that of a time varying one, right? And this all these equations are just telling you, they are just a short cut way of writing KCL and KVL at every frequency. At each frequency, KCL and KVL must be satisfied. Okay. And what comment can we make about, so that covers the right hand side. So, let us go element by element. What comment can we make about the MNA stamp of this guy? Between nodes 1 and 2, you now have, well, you have the G matrix and correct, and all right. And what must you have? A first row, third column. You have a 0 matrix, and what are the dimensions of that 0 matrix? It has to be a 2k plus 1 cross 2k plus 1 square matrix. All right. Okay. And similarly, what comment can you make about second row, third column? Basically, the currents flowing through the voltage source basically must all add there, right. So, that must be the identity matrix. And what are the dimensions of that identity matrix? 2k plus 1 cross 2k plus 1. That makes sense. And the last one, the last row, zero. What should this be? 1, where this is also an identity matrix of size 2k plus 1 cross 2k plus 1. What about last row, last column? 0. All right. So, that takes care of these two elements. The last thing we need to do is add this guy in here. What do? Plus, so G plus j 2 pi f, sorry, j 2 pi f times c. All right. And I mean, you know, though I write j 2 pi f times c, you might be wondering why this fellow is, you know, embedding the matrix between two constants, right? Yeah, it is actually 2 pi c times f, but we are used to writing, in the time invariant case, we are used to writing j 2 pi f c. So, there is no change as far as the time, periodically time varying case is concerned, except that f now is replaced by that frequency matrix. The G is replaced by the conductance, you know, matrix which captures the periodically time varying nature of the conductance, and all these other matrices are zeros or identity matrices of the appropriate order. Does it make sense, people? Right? So, how many unknowns are there now and how many equations are there? Two k plus 1 times 3 equations in as many unknowns. Right? And therefore, what do? Well, you invert the matrix, correct? I mean, at each f you invert this matrix, and that will give you all the branch currents and the branch voltages in basically everywhere, right? So, therefore, you are in a position to find all possible harmonic transfer functions from the input source to the various branch currents and branch voltages. Does it make sense? Right? So, let us say you get some V1 vector, right? What comment can you make about, and in other words, let us say, is now getting used to this notation, all right. So, let us say you want your output of interest is the voltage across the capacitor, and let us say you want H 0 of j 2 pi f. So, what will you do? Let us call this matrix, as usual we will call this matrix capital G, correct, and this is IS, okay. So, what comment can we make if you want H 0 of j 2 pi f? What will you do? You will first calculate yeah, I mean, to calculate the V1 matrix, you will have to invert the system of equations. So, notationally, therefore, it is G inverse IS, all right. So, and that will give me, what will that give me? It gives me this unknown vector which has got 2k plus 1 times 3 numbers, but which number am I actually interested in? I mean, this gives me a ton of numbers, right, but I am only interested in how many of those numbers? One of them. Which one? The k plus 1 the k plus 1th row of this is a column vector of size 3 times 2k plus 1. Correct? So, if you want h0 of j 2 pi f, for instance, is simply nothing but whole bunch of zeros, a 1 followed by another bunch of zeros. So, this should be k zeros here, and this should be k plus 2k plus 1 times 2. This multiplied by g inverse times is gives you that number h 0 of j 2 pi f. That makes sense? This is clear, folks, right? Now, if you want whatever h plus 2 of j 2 pi f, what will you do? What is the only thing that will change in this equation? Yeah, the position of that 1 will keep moving, right? Yes, something was bothering you for such a long time. Yes.
So when doing the LTI system analysis, the origin of GV equals I is the current at every node adds up to 0. Here we're extending that, saying the current at every node adds up to 0 at every frequency.
Absolutely.
How?
Oh well, KCL. Okay, the question is, why is KCL and KVL? Why does it have to be satisfied at every frequency? Does somebody have a thought on that? This has got nothing to do with linear and nonlinear, right?
We can replace it with several time invariant systems like G of 0.
No. Remember, please note that KCL and KVL are, as far as we are concerned, a laws laid down by God, right? They have nothing to do with linear, nonlinear, time invariant, time variant. All that stuff is irrelevant. KCL and KVL are true. That's it. Okay. Now his question is, why should it be true at every one of those frequencies? I mean, the fact that this network is time invariant means that the only frequencies that can exist are f, because that's the frequency of the exciting source, right? There it's very clear, well, there's only one frequency, so we're all we are one happy family, right? Now if you have multiple tones, right, the question is, why should, in other words, what he's asking is, if a1 cos 2 pi f1 of t plus b cos 2 pi f2 of t is equal to, let's call this cos 2 pi f1 of t minus cos 2 pi f2 of t. What are a and b? One and? Hey, why? Yeah. Okay. So are you convinced or you're not convinced? Two different frequencies, right? I mean, the only way the left hand side can be equal to the right hand side is if the individual ones, correct? Okay. So KCL and KVL must be satisfied at every frequency. Maybe I should have mentioned that before I went through all this, but yeah. Anyway, it's a good question, and hopefully all of you are convinced that it must be satisfied at every frequency, right? What this time variance is doing is that, because this conductance is changing with time, it's able to transfer, I mean, the fact that the conductance made this small g is not diagonal, what it means is that stuff at one frequency can, jump up or down, or do both and or remain at the same frequency, depending on this matrix, which is equivalent to saying, depending on the way you change that resistance with time, right? Frequency conversion effects can occur in that resistor. Now, it stands to reason that if you put multiple such things together and put a network, you have a complicated mess, right? And that whole mess is basically quantified by, is basically expressed by this equation, this set of equations, right? And of course, if your network turned out to be time invariant, right, you will find that, well, all these matrices will become diagonal matrices, right? And then you will find that, the only unknowns, all the unknowns except the zeroth order harmonics will all be 0. Correct? I mean, it is admittedly messy to actually do the math, but to understand at a conceptual level, what is happening is just as straightforward as it is with the time invariant case. Does it make sense, people? Okay. So now let me quickly do an example of what we should expect. I mean, I'm not expecting you to sit and invert. So, by the way, depending on the nature of this periodic waveform G, the number of, a reasonable question to ask is, what should I choose K to be, this capital K to be, correct? And that would evidently depend on, what do you think that depends on? Of which element? Yeah, in this case, the only thing that's varying with time is G, right? So, if G is basically got a lot of Fourier series, non-trivial Fourier series components, right? Then it stands to reason that this matrix would have to be of a very large dimension to be able to capture the behavior of G accurately, in which case this stuff would basically be a very large, this K would be a very large number. For example, if you had a switch, if G of t was a switch, then what comment can you make about this? The G of t is basically doing something like this, okay? And you know that the Fourier series coefficients of a square wave, and 1 by n, but the bottom line is they die very slowly, right? Because you have a very sharp edge, okay? And therefore, it stands to reason that you must consider a lot of harmonics of G of t to be able to get a reasonable representation of this stuff. So, it's not uncommon for K to be 1000, 2000, depending on, fortunately, every physical system you can never turn on a switch or turn a switch off instantaneously. There will always be some rise time and there will be some fall time, and that basically means that the higher order coefficients are falling off to 0, hopefully faster than 1 over n, right? And which is why in practice it's not uncommon to basically have this K of 1000 and 2000 or whatever. It doesn't take a genius to see that, well, the solution of this set of equations is bound to take a lot more time and effort than solving the corresponding time invariant network, right, where it's just a 3 by 3 matrix, and therefore you should be prepared to kind of spend a lot of time on simulations when you do these kinds of computations.